Hello everyone, this lesson is going to be on population dynamics, and dynamics is just referring to the changes in the population and specifically the numbers within the population and what can lead to these changes within that particular population. So lots of information that I'll even have on this first slide here. Plenty of new terminology for us. So what factors really determine the size of the population? So four major things that I have here. So kind of think of it as what can cause the population to increase in size and what can cause the population to decrease in size. And even if you think of the local population, the city population, the human population, and think what are the things that would cause the population of that city, for example, to increase. So one of them could be, well, more babies being born. So that is what is referred to as the birth rate. Or we have another kind of fancy name for that as well that I'll put in brackets here. And it is called the natality. And you should know both of those terms, birth rate and the natality. So the higher the birth rate, of course, the greater the population is going to increase in size from year to year. The other thing that can increase the size of a population is people can simply move into the population. So that is what we call immigration. Physically moving into the area. So both of these are going to increase the size of the population. Similarity, sort of a parallel with these, what would decrease the size of the population? Well, instead of the birth rate, it is the death rate. So if the birth rate is high and the death rate is low, then the population would go up. And if the death rate is higher, then the population would go down, at least if we only take a look at those two things. And just like natality is referring to the birth rate, what is going along with the death rate is going to be mortality. And the opposite of immigration is emigration. Okay, so again, the first two, they're going to cause the size of the population to go up. And 3 and 4, they're going to cause the size of the population to go down. And of course, there's a more general term for immigration and emigration. I'm not specifically talking about whether it's going into or out of, and that, of course, is just simply migration. It's not talking about the direction, whereas immigration and emigration, they do have a specific direction. So overall, what's going to determine what happens to the size of the population? I'm just going to refer to this as B, this is I, this is D, and this is E. So what is going to increase the size of the population is going to, of course, be the first two. So the birth rate plus immigration. And if we subtract that from the things that will decrease the size of the population, the death rate and the immigration, overall, that's going to determine if the population size is going to go up or if the population is going to go down. So if we're talking about more natural populations, let's say, for example, that we're talking about the number of wolves in an area. So what would cause the birth rate to go up and immigration to go up? Well, maybe there's habitat protection. Maybe there's some fencing along the highway so the wolves don't get killed, so you get an increase in the birth rate. Maybe there's more elk, the primary food, or caribou that come into the area, so there are more resources that are available. So all of these would increase the birth rate, and all of those would increase, more than likely, immigration into the area as well. Things that increase the death rate, it could be, well, possibly hunting if we're talking about the wolves. It can be a lack of food in the area. It can be habitat destruction. It can be a pathogen, a disease that's brought into the area that can cause an increase in the death rate. But if we take a sum of all four of these, that of course overall determines what is going to happen to the size of the population in terms of the numbers. Really important term as well, carrying capacity. So whenever we're talking about a natural population, there is kind of a maximum size that can be reached within the population. But here it's not just being reached within the population, it's being able to hold those numbers, being able to sustain those numbers once they are reached within that particular environment. So yes, populations, they do have size limitations. The numbers don't go up indefinitely. So growth is limited by, well, a bunch of the things that I mentioned already, but also overcrowding. That has an impact on, well, it has an impact on the number of individuals moving into the area, has an impact on the amount of food that might be available. It certainly has an impact on disease within the area, and other things, resource depletion, whether it's food or water or territory, waste accumulation, and there would be a number of other things as well that do really limit how big a population can actually get. So the number of individuals that can be reached, and not again just reached, but sustained within that population at that level, that is what is referred to as the carrying capacity. So we'll get into a few calculations here, relatively straightforward calculations. And all of these equations and the symbols, they are on your data sheet that you do have. So if I just escape out of here for a minute, and we can take a look at what that data sheet looks like. So on here, along the left-hand side, we have a whole bunch of different symbols that we have. So we'll be using this one here for population density. Capital N, number of individuals within the population, and there are maybe more than one N, an N initial, an N final, or N1, N2. Capital A is for the area occupied by the population. If we're talking about water, it's usually volume rather than area, so capital V for the volume occupied. Lowercase t is for time, delta is for change in. What I just talked about, carrying capacity, symbol is a capital K. And we'll do some calculations for growth rate, GR, per capita growth rate, CGR, and of course you should know the symbols for less than and greater than. The equations are here, so the ones that we'll be dealing with will be this one here, population density. Again, whether it's area or volume will determine which of those two equations you're picking. This is the one I kind of already wrote down for overall the size of the population. Factors that increase the size, so again, the birth rate and immigration, minus the factors that decrease the size of the population, the death rate and the immigration. We'll take a look at this one here, GR for the growth rate, and this one here, CGR for the per capita growth rate as well, as we go through a few of those calculations. Taking a look at this example here. So we have a population of deer that are living in, so whenever you have numbers, it's probably going to be important, living in this size. So this is an area that we do have here. I'll write capital A for the area. And we have two different numbers. So population of deer living in this park increased from, so I'm going to put this as NI for the initial, and I'm going to put this one as NF for the final. And from June 1st to November 30th. So we're starting at the beginning of June and we're going till the end of November. So you might be asked in terms of days, weeks, months, years, decades, but here we're going to do it per month. So it just so happens that this works out to being 6 months. If I take these two numbers here, I can calculate the change in the number. So delta N, change in the number, and that's going to be the final in F minus the initial in I. So that would be our 401 minus our 374, and that works out to 27 deer. Okay, so I haven't even looked at what I'm asked to calculate yet, but I'm still already doing some of the calculations that eventually we will need to know. So what does the first one say? Calculate the growth rate. So you go to your data sheet, you find the equation. So growth rate is the change in number, and notice that we just calculated the change in number divided by the change in time, and well, that's what this is right here. That's the change in time, 6 months. So we already have those numbers. Let's just plug them in right away. Make sure you always write the units. So we're talking about deer. So we have 27 deer, the change in for the number that we have. The time that we have is 6 months. And if you plug those numbers into your calculator, what you end up with is 4.5 deer. Again, write the units down per month. is the change that we have. So that is the growth rate. Next one we'll do is for per capita growth rate. So on your data sheet, it says that per capita growth rate, the equation is CGR is equal to change in number divided by number. And one thing that you do need to remember is that this N at the bottom, it is the NI. It is the initial number that we did have within the population. So what is the per capita growth rate? Well, if we take a look at what I have in brackets here, the number of offspring that are produced per unit time by the average member within the population, or the rate of change per individual within the population, that is the per capita growth rate. So using the numbers, so the change in N, once again, we already have that. That's the 27 deer is the change in number. Again, we're using the original number, the initial number of deer, and that was 374 deer. The units are going to cancel out, so there are no units that do go along with this one, and this works out to 0.0722 for the per capita growth rate. And the last one is for density. Here we're talking about area rather than volume. So the density, dP, density of the population, and it's going to be the number of individuals. So in the question, they would specify, are they talking about the initial population density or the final population density? Here I'll just use the final population density, and that is the 401 deer divided by the area that we have, the 12,500 hectares, and that just works out to 0.0322 deer per hectare. All right, hopefully those are relatively straightforward calculations for growth rate, per capita growth rate, and for population density. So again, we're still dealing with the changes in the populations over time, and we're going to take a look at a couple of different curves, different patterns of growth that can take place depending upon the type of population. So the two different curves, they are called the J curve and the S curve, and that's, well, kind of because of the shape of them, as we'll see. So for the J curve, what we have is rapid exponential growth. That is the key. Very, very rapid growth that is taking place. So for these populations, why is the growth so rapid and exponential? There's no shortage of resources. There's abundant food for the population, and the population, it is reproducing at really its maximum capacity. It is reproducing as fast as it possibly can, and that is what we call the biotic potential. So the highest possible per capita growth rate that population can reproduce at. So this obviously is ideal conditions, and that is exponential growth, and that is what fits along with this J curve that we'll take a look at. I'll also show this on the curve as well. Sometimes we quite often have a population crash as well, so we get a very, very rapid increase in the size of the population, and then all of a sudden those resources that were extremely abundant have all of a sudden disappeared. So resources are depleted, toxins accumulate, and now we have a very rapid die-off. What we do find is that the curve with the exponential growth, and again, we'll take a look at this when I draw it, but because it's exponential, the curve actually gets steeper and steeper all of the time, and that is what exponential growth is. All of these bold-faced terms, of course, are important. So this is characteristic of what is referred to as a closed system. So one in which it's really only the birth rate and the death rate that are contributing to the population size. We're not talking about immigration or emigration. And a classic example of a closed system would be bacteria in a petri dish. You put one single bacteria in the petri dish filled with nutrients, you have rapid exponential growth that is taking place. There is no immigration, there is no emigration. Changes in population are only due to birth rate and death rate. And eventually what happens? Well, they deplete all of their food. And then we have a very rapid die-off. It does happen with other populations as well. So usually some of the smaller organisms, so I have here insects and mosquitoes, quite often see that as well. Invasive species that come into an area. We also see it with that. So with this graph here, a population number along the y-axis over time on the x-axis. This dashed line, I'll put that in right away. We already saw the symbol for carrying capacity is capital K, so I'll put that in. This is the carrying capacity that we would have. So the maximum number of individuals that can be sustained. So what does it look like? Well, we have rapid exponential growth. Might start off kind of slow, but then the curve goes like this. It gets steeper and steeper and steeper and steeper. So at each point along the way, we can see that the slope of the line, it is getting steeper. And that is what exponential growth is. So now we've reached the carrying capacity, and what we find is they can actually overshoot the carrying capacity temporarily, but then there won't be enough resources available. So I mentioned that population crash, so sometimes this is what happens, and it goes right back down again until we reach another cycle, and those numbers would increase once again. So why is it called the J curve? Well, it's kind of focusing on this portion of the curve here, where it kind of looks like a J. And that's why it's called the J curve for that one. Okay, so rapid exponential growth, characteristic of a closed system, and it can overshoot the carrying capacity. The other one is the S curve. So with the S curve, as I have here, it starts off and it kind of looks like the J curve. So there is exponential growth that does take place, but then eventually it does start to slow down. So the populations might still be increasing, but the steepness of the curve is not as great. And eventually the growth rate is going to reach zero. And there's stability that is achieved somewhere around. It may not be exactly at, but somewhere fairly close to the carrying capacity. So whereas with the previous one, the J curve, that was for a closed system, this one is characteristic of an open system. So now it's not only the birth rate and the death rate, it's also immigration and emigration that are going to be coming into play here. Another term, environmental resistance. Environmental resistance is just a term that is for anything that's going to prevent the population numbers from getting any higher. So it might be a lack of resources, it might be crowding, it might be disease within the area. Those are all different kinds of environmental resistance. And we break it down further into what's called density dependent and density independent. Quite often the density dependent factors that can have an impact on the growth of the population are biotic in nature. And quite often the density independent ones are abiotic in nature. So what does this curve look like? Initially, again, it kind of looks like a J curve. So things might start off kind of slow at the beginning here, and I'll give the explanation why on the next slide. Then things sort of pick up. We have exponential growth. It's looking exactly like the J curve, but right around here, this is where the steepness is going to become a little bit more gentle. So it's getting steeper and steeper and steeper, and now we're going to kind of reverse it, and it's going to go like this. So now hopefully you can see why it's called the S curve, because of this shape that we're seeing here. Again, this is the carrying capacity, and once we reach the carrying capacity, it may overshoot it as well, but we have a whole bunch of things that are kind of saying, that's it. There's not enough food, there's not enough space, there aren't enough mates within the area, and there might be abiotic conditions as well, but what's going to happen is the numbers are just going to, well, usually they fluctuate around that carrying capacity. There might be a significant environmental change, and carrying capacities can change. So this carrying capacity, in fact, it might drop. And now there may simply just not be as many individuals that can survive. So we would have a die-off within the population, and they might hover around that new carrying capacity. If something does happen and it goes all the way down here, of course, now that's referred to as extinction of this particular population. So on the next slide, I just kind of break it down into this initial stage here, which is called the lag stage. This is our exponential growth. Then we have a region of stability, and then whether it's here or here, we can have the death phase that's taking place as well. Final thing that I'll talk about in this lesson is, well, it goes by a few different names, but here I have it as population life strategies or life histories. So these are the population reproductive strategies that kind of determine how rapidly a population can increase its size when there are favorable conditions, and whether they are reproducing at their biotic potential. And some populations have a natural ability, a higher biotic potential, where they can increase their population numbers really, really quickly compared to some other populations. So we'll take a look at this table here that nicely compares the two different population or reproductive strategies, the R-selected, lowercase r, and K-selected. And again, K, it is kind of referring to the carrying capacity, so it has something to do with that. So the R-selected, most of these are opposite. So environmental conditions are going to be fluctuating. They change all the time. Whereas with K-selected populations, usually their environmental conditions, they're relatively stable. So if you think especially aquatic conditions and even more so marine conditions, not quite as variable in terms of terrestrial conditions. Competition is usually not a factor at all for R-selected populations, whereas competition becomes really, really intense when you have large population sizes and it is a K-selected population. So yeah, crowding doesn't seem to have a detrimental impact on R-selected populations, whereas it has a huge impact on the K-selected populations. If there's one thing that's maybe the major factor to go by, it's this one here. Simply take a look at the size of the individuals. So if you think about really, really, really small individuals, then they are probably R-selected. If you think about ones that are much larger, then they're probably K-selected. So if we think about bacteria, R-selected. Insects, R-selected. If we talk about small plants like mosses, they would be R-selected. K-selected ones, think about the large mammals. So think about whales. Think about the large trees, so redwood trees and spruce trees. They would be more of the K-selected. So with the R-selected offspring, they grow really, really rapidly. They reach reproductive age very early on, and usually the parents don't stick around. Very little parental care. For the K-selected, again, exactly the opposite, really slow growing. So think about insects compared to whales. Grow really rapidly, very short reproductive age. Parents, well, they don't stick around at all. And if we're talking about whales or elephants or rhinos or camels or something really, really big, they're slow growing. They have a much later reproductive age, many, many, many years, and huge amount of parental care. They need that parental care in order for them to survive. Rapid growth rate. So that's kind of the key that we're talking about here with R-selected. Very, very rapid growth rate. Usually they don't live that long, short lifespan. If we just compare mammals, think about something like a mouse to something like an elk. Mice grow rapidly, don't live very long. Elk, they grow very slowly, they live much longer. And also, in the case of the mice, they all seem to, get to reproduce. But in the case of the elk, it's not all of them, and especially the males. It's only a few of them that are selected and get to reproduce. The R-selected goes along with the J-curve. K-selected goes along with the S-curve. We already saw with the J-curve that if we have a sudden change in environmental conditions, we can get a massive die-off. And yeah, this really does have to do with the biotic potential. So R-selected, they have a huge biotic potential. They can increase their numbers really, really rapidly when conditions are favorable. And for the K-selected, a much lower biotic potential. Just one final slide here. It really is a continuum. So whenever we talk about if the species is R or K selected, it should really be, well, compared to what? So if I have way over at the left-hand side here, extreme R selected, and at the other side, extreme K selected, what would be here would be bacteria. What would be way over here would be something like a blue whale. And everything else somewhere in between. So maybe, I mentioned elk, maybe we can stick elk in here somewhere. Mentioned mice, maybe we would stick mice way over here somewhere. Mention insects. Maybe we can stick the insects, and again, this is really kind of general. Insects, maybe we can stick them over here somewhere as well. So when the question comes up, are mice are case selected? Well, overall, hopefully you realize that they're small, they reproduce really rapidly, they can increase their numbers really rapidly. We would say that they are selected. But in fact, compared to insects, they would be case selected. So it should really be comparing one to the other, like I've done at the bottom here. So comparing robins and eagles, both different kinds of birds. So breeding age is how many years before they actually get to lay eggs themselves and have their own offspring. So in the case of robins, it's about 1 year. In the case of eagles, they have to live a lot longer before they even get to have babies, and that's about 6 years. Clutch size is how many eggs are laid and they hatch, and at least the chicks are born. So when we're talking about robins, it's somewhere around 5 to 6 eggs that hatch, and they're little robins. In the case of eagles, usually 1, sometimes 2 is the range. Mortality is the percentage that die. So a year after, how many are still around, or how many die in this case. So in the robins, what is the mortality? What percentage die? Somewhere around 78% is the number that I came across. In the case of the eagle, well, pretty much exactly the opposite, somewhere around 12% that would die, and the remaining would survive.